Hi, everybody. Now, you probably are muted if you're trying to say hello.
Hello.
Couple people there anyway. We'll wait a few minutes to get started still. I wanted to make sure Zoom was actually going to work for us. As you can see, I'm on campus today. It's kind of creepy. It's very quiet. There's nobody around. Smoky. You can go ahead and unmute yourself to say good morning or whatever. I saw someone said morning in the chat box. So hopefully, like, we have 5 minutes still before classes. Well, it's funny, you know, classes officially already started because it's scheduled to start at 9:30. But I think we would lose our minds and be exhausted if we tried to Zoom for the entire time this class is scheduled. So that's why the abbreviated time frame. So just an hour and a half, that's plenty. And I'm going to stick around after class anyway. We'll officially end at noon, and I'll stick around until 12:30 if people have questions or you need an ad permit or something like that. And I'm going to repeat that in a little bit when more people sign on. If you haven't already, but you probably have because you got here, gone to the iLearn page to discover the syllabus and the Zoom meeting link. There's the syllabus document that's a PDF that I put in the course documents at the top of the iLearn page. Actually, I'm going to share the screen so you guys so I can point out what I'm talking about. So, okay, so what I'm talking about is, here's the syllabus that I put together. I tried to use the university's sort of automatic system to create a syllabus, which I thought would be handy because it should pull in the course description automatically and all the automatic notices that you're supposed to have, like all these policies down at the bottom of the syllabus that are supposed to be in every single syllabus that you get. But it's not very flexible, and it didn't have places for me to include a lot of the material I wanted to. We'll go over that in more detail later, but notice there's a link from the syllabus, but also from I guess we'll focus on the course document part here. A link to the textbook, and which is free, so save you like a good 60, 100 bucks or more. I don't know how much they'll charge anymore. I always choose an old edition, or I have chosen old editions because the updates are never really significant. But I found in the last several semesters that I'm able to, I'm a little short there. I'm able to find free textbooks that are high quality, and why not use them? And I really like this one because it's got a lot of interactive elements to it. It is, it contains it's got nice summaries, very specific learning objectives, quizzes at the end to test your knowledge. It's got they're like micro quizzes or mini quizzes every page or two, sometimes less, with just like 2 questions or 3 questions that quizzes you on what you just read. And I think that's good, because what better way to test whether you got what you just read? Anyway, that's a handy resource, I think. So I really like it. And it's got, you know, you're already online for class, you're already online for a lot of the activities, so your textbook's online. It's got links to videos, like instead of, you know, one of those call out boxes that you have in a textbook, it's got like a video link that's right there, so you just watch the video. And yeah, it's pretty cool. The one thing I do ask you though is to go to this site and purchase a small kit of rocks and minerals. It's a pretty good deal because you get 30 or 15 rocks, 15 minerals with it. And I've postponed looking at rocks and minerals in the class to week 6. We don't start that. And that's in order for you to give you time to go to this site and to order everything. The one thing, you know, when I called in the summer and asked about it, the shipping time to campus was only about 3 days. And that has gotten longer, especially with the whole US Postal Service slowdown and all of that. So don't wait until the last minute. Definitely jump on that. And I really hope that she also doesn't run out of these. If so, there are other sources. So let me know if you have any trouble getting those. Good morning. I'm seeing more people arrive. You automatically show up with, I think it was you're muted and your video's off. You don't need to share video if you don't want. It would be really great though if you guys would put your picture or some kind of image that represents you instead of your name, because it's a lot more interesting to like look to somebody's face, or, you know, instead of your name on the screen in a black box. So that's cool if you could do that. Again, it's not a requirement, you know. I'm guessing some of you still in your jammies, right? I would be. Okay. So I'm going to start recording so that if I can figure out how to do that, I haven't recorded in a while. I will take anybody's help when it comes. Oh, I see it. Oh, I think we are recording. Never mind. It automatically started. We're good to go. Okay. So it's 10:32. I'm thinking that it's going to take people a little bit of time to get here. I want to give it just a couple more minutes before I really officially get going. 10:35 is when I'll call it. The deal with this class is that I don't want to meet for 2.5, 3 hours at a time. That would be awful. I guess I should introduce myself first too. I'm Mary Leach. I'm a professor in the Department of Earth and Climate Sciences. I'm on campus today. I came to campus to make sure that I had everything that I needed, and I'm gonna be teaching from here on Tuesdays certainly, so that I have access to materials, rocks and minerals and maps and whatever I need to show you guys. I'll get into a little bit more about the class, but I just wanted to say, like, we're gonna meet from 10:30 to noon on Tuesdays and Thursdays. That's when the synchronous class will be held. You can take this class asynchronously, so you don't need to show up to these sessions if you can't. But I really, really encourage you to, because I think you'll get a lot more out of the class. And I think it's like, especially like now when we've been pretty isolated, I think it's good to have some human interaction too. So yeah, definitely you get more out of the class by being present. So I encourage you to come, but you don't have to. You don't need to give me any excuses if you're gonna miss, if you're normally there. It's nice to, you know, have an email that says, hey, I'm gonna miss class this day. Please, can you keep me in the loop if there's something more I need to do? Something like that. But you really don't need to, because everything's gonna be on the iLearn page. There's gonna be a recording of the class. So if you miss class, just come back afterwards. You know, it's gonna take me a little bit of time after, you know, I'd say by 1 o'clock, 2 o'clock certainly, the recording will be on iLearn and you can watch anytime afterwards. So Tuesdays I'm gonna set aside for lecturing and doing short activities, but sometimes, not always. I'm gonna save the labs for Thursdays. Same deal, 10:30 to noon. And if you can't come, that's okay. I'm hoping that all the labs will be self-explanatory. So you should be able to download the document from the iLearn page, print it if you need to, but I'm actually uploading the Word documents that that you can open in Microsoft Word. If you don't have Word, that's okay. I think you can open those files in pretty much any text program, certainly Google Docs, right? Or if you use Pages, if you have an Apple, you can use that. Then you can just type your answers into the boxes, and you don't have to print things out and write on them and then scan it to upload it. You get my drift. So I encourage you to do it that way and save paper and all that. Okay, so Tuesday's lecture, Thursday's lab. Sometimes, I don't know that it's going to be every week yet. I'm building this class from the start, from the beginning this semester. It's the first time I've taught this class. I've been teaching for a long time, and I've taught material like this in other courses before, like in the Violent Earth class for natural hazards. That comes into play a lot in this class. And plus, that's some of the more interesting stuff to learn about, I think. Anyhow, I'm building this from scratch, essentially. The content that's on iLearn is what I have so far. I think I've got most everything for the first 4 weeks on iLearn now, but I'm going to be tweaking things. This week we're good to go. We're ready to roll, but like, give me a little bit of time before you try to do any working ahead, if anyone's going to try to do that. You don't need to, right? I mean, especially if you're going to come to class, hear what I have to say, and then try to do the assignment. I know this is, for some of you, this is the very first earth science class or geology class that you've had. Others of you have experiences in your past that are related to earth science, or maybe you took earth science in high school. Otherwise, it's been like since 6th grade, since earth science was the focus of your K-12 science education. So slow me down. I haven't taught a GE class in quite a while. While this class is designed for majors, actually, it's a general education course that's designed for majors. So it has more units devoted to lab than does the standard introduction to geology class, which is called Our Dynamic Earth. That's really the only difference. It's a 4-unit class, and one of those units, no, it's 2 of those units are, it's 1 or 2 of those units are lab units. It doesn't really matter. It's all funny anyway, because I'm going to divide the class the way that I think is best for your learning. So that's why we spend half our time in lab and half on lecture, essentially. I'm getting just onto tangents here. Let's look at the iLearn page that I've been talking about so that you can see. Oh, that's what I was going to start to say. In some cases, we will have pre-labs, which means after class on Tuesday or at the end of class, I'll talk about what we're going to be doing for lab. And there's a pre-lab assignment that kind of gets you thinking, has you do a little bit of reading, like literally there's 2 pages of double-spaced text that I'm going to ask you to read. That gets you ready for lab on Thursday. Usually it's closely related to lab on Thursday. Sometimes it supplements the lecture. It's going to serve both purposes to kind of like help seal in what you learned in lecture and to prep you for lab. Okay, let's go to the iLearn page. Let's see. I'm getting out of here. Okay, so, oh, you're already looking at that. I was looking at you guys. You were looking at iLearn. Okay, so up here at the top, course documents. Number 1, I've put a question and answer forum there. I'm hoping that if you've got questions about the course, either the logistics of how the course runs or where documents are, or even if it's about the content, go ahead and post the questions there. That way everybody can see both the question and the answer. I guarantee you if you've got a question about something, somebody else has the same question. So it helps everybody. If it's of a personal nature, go ahead, shoot me an email. But if it's just a question about class, please use the forum. Here is the syllabus. We'll look at that in more detail later. It contains the schedule of lectures and labs. Right now, I'm planning on hitting on every single chapter in your textbook. I think that might be a little ambitious. So let's see how it goes. If something drops out of the schedule, it will be toward the end of the semester anyway. And if we do that, it's only to give us more time on the more fun, the cooler geology that we'll want to work on. I'm thinking more like more time on plate tectonics and the rocks that are associated with them. Okay, so let me spread this out. Okay, so that's the syllabus. The textbook is awesome. I'm going to take you there right here. This is the textbook. It's got links to the start of each chapter. Where this week, what we're going to talk about relates to scientific literacy, understanding science and what science is, what's the scientific method, how does it all work, and then start talking about how the earth works. But just to give you an example of what your textbook, how it's formatted, you get the learning outcomes, like these are the goals of what you should get out of this chapter when you're done with it. It's relatively brief. This is not an overly wordy text. So I think you can manage it with all your other work. A couple pages of text, and here's one of these little brief quizzes where it asks you a question, you answer as best you can, and you check your answer. I'll just click 3 random answers because it says select 3, and it says, gives you some feedback about how you went awry. you can go back and try the question again. These are similar questions, but not the same as the ones that you'll see at the end of the chapters. Here's another set of reading and another one of these mini quizzes. So again, it has you, if you can't stand to read an entire chapter in one sitting, you can sit down and just like do it by section, quiz yourself, and like bookmark it and come back to a particular section. Here's a third quiz, a fourth quiz. This doesn't have any videos that I'm noticing, but it's got a lot of interactive diagrams. You can click on these and it will enlarge them if you ever need to see a bigger version. That's another reason to go with the online textbook, is if you can't see something, click on it and enlarge it. Another, a fifth one. Oh, there's a video. Neil deGrasse Tyson. Blah, blah, let's see. Another one. Holy moly. Finally, we're at the end. It's got a written summary of what the chapter was about. Again, really brief. And then there's an end of chapter review quiz. And these are like 12-ish questions that you can answer about what you just read and make sure you got it. Now, I think like that was super brief, and you can totally, I think you can find time to do that reading, and hopefully before you come to class on Tuesdays, that will help you get ready for the lecture. Now, what I talk about in lecture, though, is not necessarily going to be the same as what you read in the text. They'll be related, but not identical. So they really do complement each other. Okay. I mentioned this earlier, but for people who are just showing up, for week 6 of this class, so don't, try to get this done in the first few weeks. Purchase this kit of rocks and minerals. It's from some homeschooling website. That was the best price that I could find, and that included the largest number of rocks and minerals. So it's a set of 30 total for $30. Considering your textbook is free, I hope that you find that a reasonable cost. Oh, also, the department won't collect a course fee for this class because you're not here on campus and because we're not buying supplies for you. So no course fee, it's just this $29.50 plus tax and shipping if you have to, that you'll need to spend, please. This is the Zoom link that we'll use every single day. It worked today, so fantastic. It keeps it simple, right? You don't have to scroll to the right week and whatever. We'll just always meet here. Okay, and then each week I will leave you a set of links or documents. This is a page, so the lab documents are on the separate page, and you can click on the pre-lab handout to download that. This is a video that you should watch for the pre-lab, and then there's a part 2 that is the actual lab that we'll do on Thursday. So they're all sitting there waiting for you. This is a quiz, a weekly quiz that I'd like you to take that is related to your textbook reading, and again, peripherally to the lecture, but not directly to the lecture. As I add more questions and as we kind of work our way through the class, there'll probably be more that relate to lecture itself. This week, I've got a survey that I'd like you to fill in that I ask you a few questions about yourself, like any nicknames, like what do you want me to call you? Because the name that's on the roster isn't necessarily the name you want me to call you. I want your pronouns. I'd like an address, a mailing address for where you're gonna physically be in 4 to 5 weeks, because the department is going to send you a small box that contains a small magnet, a glass plate that's a thick glass plate, and hopefully a dropper bottle with a little bit of 10% hydrochloric acid in it. We're getting permission from the health and safety people, risk management and all that right now. They may nix it. They may say we can't send it out, in which case we're stuck with lemon juice, which doesn't work really. I'm trying to fix it for you guys. That's so you can test for calcium carbonate. It fizzes when you do that. When you drop a bit of acid on it, it breaks up that ionic bond. Okay, so what else? The survey, and it asks you like if you've got any documentation from the DPRC, if you need like extended test time or any accommodation like that. It gives you a place to upload that document and to just leave me any notes. This is all between you and me only, so feel free to communicate whatever you like in those surveys. Same thing each week, right? There's some lab documents and a quiz. The lecture's not there yet because I'm giving it right now. As soon as the lecture is done, there'll be a recording, and I'll put a link to the recording there. It'll probably end up on YouTube or Google. Right now, I'm putting a bunch of these documents on my Google Drive, and I hope, I realized last night I got an email saying like they needed permission to access the document. I hadn't done the right kind of, I hadn't give you the right kind of link. I fixed that, I hope, and now you shouldn't need special permission to access those. Okay, I feel like I'm talking so much. That is essentially the schedule for the semester. We are covering a lot. Right now, there is no final exam, and I think I might keep it that way because I'm trying to make, like, the quizzes are not worth they're, I think, a total of 20% of your grade, the ones that you take weekly. I want those to be low stakes so that there's no test anxiety, that it's like not everything, your success in the class is hanging on one exam. I want it to be spread across the course. And so the vast majority of the credit, it's like 50 or 60%. We'll look at the syllabus. 50 or 60% is for your labs. So that's the most important thing I want you to do, is to do those labs and understand them well. We'll probably do some in-class quizzes that are different from the weekly quizzes. And I think maybe one every 2 or 3 weeks. How about every 3 weeks? Something like that. We'll figure out a schedule like that, and we'll use those instead of a final exam. So I think probably you're silently cheering out there. I'll just imagine that in my head. Okay, I'm gonna stop sharing the iLearn page, and what else? We've looked at the textbook, we've looked at iLearn. Okay, I can get rid of that. Why don't let's have a quick look at the syllabus, since we've been talking about it already. Again, this is right there on iLearn, so you can download it and look at it on your own screen if that's easier for you. Okay, so I put in here, this is the official class schedule, right? 9:30 to 12:15. That kind of gives you an idea how much time you should be spending sort of actively working on getting ready for class, doing the pre-labs, being in class, not necessarily completing your labs. You might need more time than that as like a as your homework instead of completing them live on camera with me. My plan is to get you started and to make progress on your lab. And if we finish, great, but there's only an hour and a half, and some of these labs are a little bit more involved. But I want to get you started on them because they ask you to, in the first few weeks, I ask you to use some new tools like Google Earth. If you've never used Google Earth before, we're going to use it in some new and exciting ways, I think you'll see, especially when we get to the plate tectonics. I found some new KMZ files that we can open in Google Earth that will really help to visualize the plate boundaries and earthquakes and volcanoes and all that. It's like it's a sweet, sweet lab. Okay. So synchronous times 10:30 to 12. I know I'm repeating myself a little bit. I just want to make sure everybody heard it. I still see people like popping in every now and then, or I'm seeing you turn your screens off. I'm not really sure. Office hours. Okay, so the time right after class, 12 to 12:30, is a time where we can work together face to face. I hope to get the notifications from your Q&A forums. Like if you post a question, I should be able to get an answer to you right away, or to the forum right away. And so I'm hoping that will be sort of like a rapid response kind of office hour when that happens. But that's just randomly. So I'll just try to do the best I can with the forums. Give me at least 24 hours though for a response to an email. Sometimes like it's my whole day is just like meetings and Zooms and class and everything, and I don't get to my email until late at night, and so it might take me a while. I usually do better than that though. Okay, but if you want an appointment at other times during the week, if this doesn't work with your work schedule or whatever, that's fine. Just send me an email and we'll set something up. This is the description in the course bulletin. I changed this to say, okay, it's 1 unit in a lab, to say no field work because we can't take field trips. It's a pity, but with COVID-19, we don't have permission even to bring people to a site in the field and to be physically together in the outdoors, which is a real pity, and it's impacting our majors courses right now. Hopefully just for 1 semester. And then, like I said, where there was supposed to be an extra fee that was required for the class, for the lab, there's no fee that's going to be collected. So what are we going to do in here? We are going to have lectures on Tuesdays, lab on Thursdays, but asynchronous is totally fine. You're going to have the lab each week is going to relate to the lecture and to the reading topic, so they're linked. We're going to have these regular weekly low stakes quizzes. So I think I set them to 20% of your total grade. Those are on iLearn. They give you immediate feedback, and it should keep you current with the course if you're doing them every week. They get kind of lengthy. When I finally put them all together, they get up to like 30 questions, but you will have seen some of them before from the text, so it should go kind of quickly. And hopefully if you've done the practice quizzes in the textbook itself, you'll be ready to take these quizzes. What I was also going to say is I do not limit the number of times that you try to take the quiz. You can take it as many times as you want, and it will accept your highest score. I'm trying a new thing though, the way that it grades, that if you do take it more than once, it dings your score a little bit. I don't know how to control that. I'm gonna see how it goes. If I don't like it and it's dinging you too much, then I'm gonna switch it back and I can regrade the quizzes. So no worries there. Interactive quizzes. I hope every week to incorporate different faces of science, not just old white men. I'm hoping that you will see yourself in the faces of the scientists that you become familiar with in this class, and could actually see yourself doing some science. Because believe it or not, anybody can really do science. And I hope you'll feel more and more like that as the semester progresses. I put together, this was a really hard task. This is like the shortest of a list I could come up with. It started like with 100 of these, and I got it down to 30, and this is the best I could do. Whatever, it might be at like 15 right now. This summarizes everything that I hope you to get out of this class. Some fundamental problems of like what the scientific method is and understanding what goes into science, the field work, the laboratory analyses, the experimentation, the just observations that are made in all those environments that are all part of the scientific investigation. I hope that you will learn to communicate in writing and also with diagrams or graphs or even drawings. Drawings can convey a lot of information, and I really encourage you to answer questions with a drawing in your labs, even as part of these quizzes. If there's a place where you can express yourself that way, I'll definitely leave you a place to upload a sketch. And use colors, right? And you can annotate and draw arrows saying this is that and that's this. Drawings are great. I want you to, so in those labs, you're gonna solve some actually like real problems. They may be simplified for the class, but they are real geologic problems that we're gonna be working on. I want you to understand geologic time. It's a different scale. It's a whole different scale than regular time, and it takes a different kind of thinking. I hope that I can convey a bit of that to you, and then we'll talk about the relative dating methods that were used to establish the order of the different layers of rock, and then how we discovered different life forms at different time frames in Earth's history, and how we put that together to explain the evolution of life on Earth. A little bit of that. I'm not a biologist, I'm not a paleontologist, but we'll look at a little bit of how that was used to create the geologic timescale. We're going to look right away, even today, if I stop talking about the syllabus, the composition and the rheology is like the physical state, like whether something is a solid or deforms plastically or is a liquid, that kind of the physical state of the different layers within Earth's interior. And the different processes that are going on in the core, the mantle, and the crust. We're going to focus on the crust for the most part, but we certainly, plate tectonics takes us down into the upper mantle frequently in subduction zones. So mantle becomes part of the story that we're telling. We'll cover hotspots for sure. We're not going to leave out Hawaii or Iceland. Definitely going to talk about plate tectonics. That's my thing. I have a few slides to show you the kind of geology that I work on. But when it comes down to it, I want to relate the minerals that we're going to look at, the rocks that we're going to look at, all back to plate tectonic processes. What's going on at subduction zones, where some tectonic plates are driven down deep into the mantle, or at mid-ocean ridges where there's spreading taking place and new crust is being formed. Transform plate boundaries, we've got one right out there. The San Andreas Fault is one of the like great examples of a transform plate boundary. And I'm going to show you that over and over again in different ways. We're going to look at Earth's materials, like I explained. I won't go over that again. We're going to start in the first couple of weeks with topographic maps, and we're going to look at geologic maps. We're going to look at satellite imagery. You're going to make cross sections into the upper part of the crust. We're going to look at structural geology, which is like how the brittle deformation and plastic deformation that takes place in the crust, how that works, how that plays into plate tectonics. What else? Definitely natural hazards. So volcanic eruptions, earthquakes, and seismology that explains like the spreading of seismic waves. We're going to look at tsunami is going to come into play. We're going to look at we'll talk about, Katrina is going to be part of that. This is a hurricane and storm surge. Why am I blanking on my hazards right now? Landslides, mass movement. So like rock falls, landslides, creeping earth. We're going to look at all different rates of that kind of deformation and how the societal impact of all of those things. Let's see. Oh, floods too, of course. We will get into surface water, like rivers. We will talk about groundwater somewhat and how it and what pollution looks like in the groundwater. We'll talk about weathering and erosion, wind, water, and ice-driven processes. So that's glaciers too. So we'll touch on all these different environments, rivers, coastlines, deserts, glaciers, after we talk about the fundamentals, after we get through talking about Earth, the Earth's structure and composition, after plate tectonics, after we look at Earth materials, then we'll get into those processes. And then hopefully there will be time to talk about mineral resources, fossil fuels, and aspects of climate change, because I think that's probably pretty important for everyone. Okay. I'm not going to read all this. This just says, please use the iLearn page, go to it frequently, and also use your sfsu.edu email. That's the one that you use to log into iLearn. And as long as you're using that, I can communicate with you because that's the email address I have. And if I send something like an email through iLearn, you'll get it. This is about the textbook. I just explained that. I explained, here are the details for that rock and mineral set. This just says, the material that I've compiled for the lectures and for the labs is kind of in the fair use domain of using other people's work. I'm giving credit to the people who designed some aspects of your labs or the images in your lecture. Just realize that and don't spread it yourself, please. Certainly, I mean, if it's for education, right? That's the whole point. The idea is like, don't try to make a buck off of it. That's all it says. Participation. This just says, please come to class if you're able. If you can't, because I think it's going to be really worthwhile to come to class and to just interact with everybody. It's not going to be just me lecturing, right? I hope to like have you guys working in groups as soon as I can figure out how all that works with Zoom. I've been doing Zoom meetings all summer though, so this is getting almost to be like second nature. Okay, Here's the grading policy. Okay, so standard sort of grade breakdown that you've seen before. The weekly iLearn quizzes, I put those at 20% of your final grade. The weekly labs at 50% of your grade. And the exams, I already said no final exam. So these exams are these longer quizzes that we'll do either timed on your own time, it'll probably be that, because I don't want to like give up class time to an exam, honestly. I'd rather you have that, do that offline. Online, but later. Those I think will work out to about 30%. I think this is how it's going to work. This is what we're going to start off with. If there are any changes in the course of the semester, if I feel like I need to adjust something to make it better, a better representation of your learning, then I'll do that. But let's work with this for now. Then I've got your schedule. This simply gives the dates of the week. So Tuesday is the lecture, Thursday is the lab, and it gives you the topic. This is the corresponding reading. I don't exactly go in the order of the textbook, although the order is very good in the textbook, because I wanted to bring some fundamental like Earth history and geologic time stuff up to the beginning, because that's important. And I needed to bump the minerals and rocks back to week 6 so that you guys have time to get those kits. I've explained all that. This link, you may see again, Science Daily, is a great place to just get it's like a compilation of all the science news that's happening in the world. And if I ever refer you to needing to go out and find an article that's about something that's going on right now related to geology or hazards, this would be a great source. Here are some deadlines, just so that you can think about it. We don't meet on Labor Day, but there you go. The ad drop deadline is, let's see, that's 3 weeks from now, isn't it? They are making withdrawals easy now because of the pandemic, right? Trying to take it easy on you. And they even let you, like, what is the last? I saw that one of those dates was really late. Through to, if you had documentation of a serious reason, you can do it in November all the way through to December 11th. So that's pretty impressive. There we go. And here's some resources. Food, housing resources, if anyone needs links to that. The disability access policy. This disclosure of sexual violence. And just a promise to you here, this is just from me to say that I want this to be a respectful environment. Everyone should be using everyone's preferred pronouns and their chosen name. And that I want to incorporate these diverse profiles that I've said of scientists. So BIPOC, LGBTQIA+, and even women scientists, because we're a minority. Certainly in academia, women at the higher, like at the professor level where I am, we only make up about 20% of the geologists working in the field. So it's not great odds always. Our department's great though. Right now, we've lost some faculty recently to retirements and to moving to other opportunities. And now we have a really high women to men ratio in the faculty. And then this final thing here, if for some reason I drop off the face of the earth, or if you've got a problem that you can't address with me and you need to take it to the department chair, you can email geosci@sfsu.edu and get help that way. I'm just thinking, like, if COVID strikes and I'm quarantined in a hospital and like you can't get a hold of me. So that's why it says if like I am unresponsive for more than 5 days, that's a whole week. Okay, I'm gonna stop sharing that document. Whew. Okay, are there any questions? Feel free to unmute yourself or raise your hand in the window. I can see most of you that way. if you've got questions about how the class works. I'll just pause for a moment. Oh, I see there are things in the chats. Okay, let me read those questions. Okay. Can you repeat the readings? Yeah, the textbook's there for you to read whenever. It's not like a one-time use thing. Are you thinking, I'm not sure what you mean, actually. Does the survey work for anyone else? What do you mean? Do you mean people that aren't registered in the class? Anyone who has that link from the iLearn page should be able to take that survey. I'm surveying you guys so that I want to know what your future goals are too. And in this online environment, like, it's hard to have those conversations or to just break up into smaller groups and talk together. Oh, I see. So the survey doesn't work for somebody. Okay, there's a problem. 2 people said there's a problem. Okay, I will look at the survey and I will fix that today, and I'll extend the time to take it to 2 weeks instead of just the first week of class. Whenever. I'm just trying to get answers to the questions early on. Is there a certain day of the week that weekly quizzes are due? No. My goal is that you get them done by the next week's class so that you don't get behind with the material. What I don't want you to do is like miss several weeks and then try to catch up all at once. It's just harder to do that way. So if you keep it in these small chunks by doing the relatively short amount of reading of one chapter and those quiz questions, then it won't be such a big deal to keep up with the material. Okay. Oh, and also, so you can take the quizzes as many times as you want. The highest score stays. Try to do your best on the first run though, because repeat runs, because you get you see the feedback, it takes some percentage off. I don't know that yet. If it's too much, I'm going to fix that. But you see enough feedback, I think, if you get some of the correct answers, that it's fair to deduct a little bit. 5%, 10%, something like that, not big. Okay, they are open until the end of the semester. So if you can't do it a particular week, do it the next week. I am not gonna keep track of you. I'm not gonna ding you if it's late, even though I've suggested it's like do this week and start the next one the next week, whenever you can get to it, because everybody's lives are all turned upside down right now with jobs or no jobs and blah, everything. Just do it when you can get to it, right? Okay. So you don't need to email me if you're gonna be late with it. Just do it when you can. Should we annotate your readings and submit it? No, you don't need to. That's all for you. If you want to annotate your readings, super. Keep those as study notes. Certainly, you could use those notes to help take the quiz. Submit it. Okay, so I get the survey doesn't work. I don't know why it didn't work. I did it late at night last night. That's probably why. If you want to annotate the reading online, there's a Google Chrome extension called hypothesis.is that you can annotate directly on websites, and it saves it for you so you can annotate the online textbook. Awesome. Thank you for that tip. I just discovered that today. I can't annotate the slides in Keynote when I'm doing the lecture slides. So I'm going to have to find a Chrome add-in or something to solve that problem. But today it's not solved. I checked the first quiz and it says we are only allowed 1 attempt. Grr. Okay, I will fix that also. Don't try to do the quiz during class, and don't try to do the survey during class, because I just want you to like listen for now. I promise right after class, thank you for the link, Kay. I promise to fix the survey and the quizzes. I'll go through all the quizzes and just make sure that it says unlimited attempts. This is great. Thank you, and let me know if any of this comes up. Outside of class, the forum is a great place to just post that so that if you see it, everyone else will see it, hopefully, and there don't have to be 30 people sending me emails. It can just be the one notice. All right, any other questions? Feel free to unmute. Feel free to jump in here.
Are any of the lab works going to be group work, or just are all the lab works going to be individual?
Because you're dying to do group work, right?
Well, it's more, well, like, yeah, but it's just more like a curiosity. Yeah.
Right now, no, it's not. And part of the reasoning there is so that the class can be done asynchronously. If it requires group work, then it's hard for someone who doesn't come to the lab section on Thursday to participate in the lab. So I'm trying to mix them up so that you can do this individually. Now, it doesn't mean I still might put you into groups to work together on the lab. That's a definite maybe, probably, when we get started. We'll find out on Thursday. But no, it will not be required. Any other questions? Okay. Oh, that clock is dead. No wonder so I keep looking. I'm like, the time is just going nowhere. It says 10:20. That's not right. It's 11:20. Okay. So we have about 40 minutes for the rest of class. I'm not trying to fill class. Like, I feel like I got to get a lot of stuff done and we got to get through all this material. I just want to use our time that we've got together this week. So I have a lab ready to roll for you on Thursday. There is a pre-lab, so please do work on that. You can just grab that after class, or if I remember, I'll pull it up and I'll show you what to do to start. But there are instructions on the pre-lab that are pretty clear, and hopefully you can follow through those. Okay, so if there are no more questions, I'm going to share the lecture slide and tell you, I'm going to start by telling you a little bit more about me and the geology that I do. I find that like I forget to do that, and so I'm just like some random person thrown up here. So I might as well like explain a bit about my background. I've been at San Francisco State for 15 years now. I usually mostly teach majors courses or grad courses, and this is the first time I've taught a general ed lower division class in a while. But I've been excited to teach this class because I usually meet students when they're juniors or seniors, and I want you guys, there are a lot more freshmen and sophomores in this level of class. And so I wanted to come talk to you guys and teach this class to see if I can't talk some of you into even deciding to major in earth sciences, earth and climate sciences. So I'm gonna, during the course of this class, I will talk about careers and point out the different ways that you can do geology as an actual scientist. Just so it's on your radar, mostly. Okay. What else? Let me go to the slides now. Share this. Okay. I am going to keep this in the, I'm not going to use the slide show mode because in slideshow you can't see my pointer or anything, and so I can't point to anything right now. Until I solve that problem, we'll just use this mode. So this is what we've talked about a little bit of how the course worked, and for chapter 1, after I introduce like my background, I'm going to go into a little bit about why we study the Earth, and talk about the scientific method and how do you know what a scientific fact is. And we've already talked about the textbook, so I don't need to highlight that anymore. Okay, so I am a Bay Area native. I grew up in the South Bay in Campbell, and I went to San Jose State for my Bachelor of Science in Geology, and then went straight to grad school. I went to Stanford and did my PhD there. No master's. You don't have to do a master's in between. You can, depending on the field, you can go bachelor's to PhD. And that's mostly because if you want a PhD as your terminal degree, then you just go do the PhD. If you want the master's as your terminal degree, you go do that. It's less the sequence. The kind of geology that I do, the subfield that I work in, is igneous and metamorphic petrology. So I study igneous and metamorphic rocks, and pretty high grade, and that means high pressure temperature rocks that are from the middle crust or the lower crust of the Earth, in particular where continents collide. So I started off, I'm showing you a picture of Chomolungma, Everest, right? Chomolungma is its indigenous name. So I suppose that's the name that we should call it, just like Denali is the indigenous name for, oh my God, I'm gonna forget the English name of it. That big mountain in Alaska. Someone help me. It's okay, it'll come to me later. Anyway, so I visited base camp here in Tibet. China would claim it, but it's Tibet. And this is a rock glacier down at the bottom. You can see just behind the tents, you see this lump here that's kind of whitish at the front. That's a glacier, and it's called a rock glacier just because it's covered with rock. And that's coming down off of Everest. And we were just there on a spectacular day, as you can see, like, oh my God, it was like one of those moments when you just like want to fall to your knees and be like, oh, it's Everest, I've finally seen it. It felt like that. So that was pretty cool. This was part of a project that I had for about 10 years in the Himalaya and the southern Tibetan plateau. Mostly I worked in India, and so the western Himalaya, but this was one time I got to the eastern portion and picked up some rocks there to work on in the lab. What these are is on the right. This is this is an image down a petrographic microscope. So it's a polarizing microscope that you study a very thin slice. It's a 30 micron thick, so that's a millionth of a meter thick slice of rock that's on a glass slide. So basically you glue a hunk of rock to a glass slide, you trim it off so that it's pretty thin, and then you end up grinding it down until it's 30 microns thick. And when it's that thick, you can use the optical properties of the individual minerals to tell you a lot about the rock. So you can either do it yourself. I'm looking at a machine right at the back of the classroom that will let you make a thin section. It's just a lot of elbow grease that goes into it. Mount McKinley, thank you. You could have unmuted yourself and just jumped in. That would have been fine. The textbook is at the very top part of the iLearn page, by the way. And these slides will definitely, oh, you want the slides separate from the recording? Yeah, I can do that, no problem. I'll put the slides and the recording on iLearn after class is done. But you're not gonna get them ahead of time because I'm putting this class together on a week-by-week basis, basically, because it's the first time around. Okay, so what we're looking at are the QZ represents quartz. You've heard of that mineral, I'm sure. And we're looking at a couple other minerals. KY is kyanite and SIL is sillimanite. And we're just looking at relationships that in that case that the kyanite grew over the sillimanite. And we can use those relationships to say, all right, this mineral grew first and that mineral grew after. You're gonna do look at some relative dating technique exercises in your lab in a couple weeks that will do the same kind of thing for different layers of geology. Anyway, so we study the rocks down a microscope. That's one of the first things you do. Or you can send it out to a lab for $40. They'll do it for you and it'll polish up. And so after a field season, you're left with, let's say, 50 to 100 thin sections that you're using as your set of microscopic evidence that you'll use. And this diagram over here, the pressure temperature, says pressure on the y-axis and temperature on the x-axis. And then all these colorful fields like eclogite, granulite, amphibolite, those represent like groupings of like similar minerals that grow at those pressure and temperature conditions. So basically this represents the blue and the green represent like a subduction zone, crust going down a subduction zone. And the green schist, amphibolite, granulite represent crust that might be caught up in a continent-continent collision, like in the thickened crust, the thickened middle crust or lower crust of the Himalaya, somewhere like that. So this diagram is sort of a basic tool for you plot, like you're trying to establish the pressure temperature conditions of the rocks that you're studying as one of the pieces of information that you use. Of course, there's field work. I probably should have started with that. This is my ex-grad student, Jack Reeder. He finished. He didn't quit or kick him out. We're in the Adirondack Mountains in upstate New York here. There were a lot of mosquitoes, so he's got a mosquito, or no, they weren't mosquitoes. They were like just little biting bugs. So he was protected from that. But he's collecting a rock with a sledgehammer and a chisel right there. And, you know, that's kind of where it starts. So we're looking in the field, we're studying the rocks in the field at a macro scale, collecting samples, looking at structures, measuring the way the rock dips and the way that the rocks are oriented. Looking at faults, looking at shear zones where the rocks have deformed plastically because they were hot. All that kind of stuff you're doing in the field. Getting global positioning system, GPS coordinates to identify like the exact location of these rocks and structures. And the whole idea is to kind of put it together to get a tectonic diagram. Like what does this is a geologic map of like the Grenville in New York all the way up into Canada. And it shows the major different rock layers. And a cross section through that might kind of give you an idea what happened in the past when these continents collided, and we're talking 1 billion years ago. These rocks are the oldest. Going from the Himalaya where things were happening like 50 million years ago to working on rocks that were active 1 billion years ago is kind of crazy. But we can reconstruct the same kind of stories from 1 billion-year-old rocks as we do from 50 million-year-old rocks, which is cool. We take the thin sections of the rock to labs like this one. This is an electron microprobe. So over here on the left is the actual microprobe. And these are all these detectors. This is an electron gun that's pointing straight down, and that points at your thin section that's down in the sample chamber there. And then these things are the detectors that catch the X-rays and the energy that's coming off of wherever that electron beam is hitting on your sample. So if you're analyzing a quartz grain in your thin section, for example, those detectors will say it's got silicon, it's got oxygen, and then you can deduce that it was quartz. And it can also give you quantitative analyses. So that have very small errors. So we can use the mineral compositions to tell us things about, again, like the history of these rocks. I've used another instrument a lot. This is called, its acronym, the shrimp, doesn't really give you a good idea of what it really looks like. This device takes up a really large room. It's not shrimpy at all. In this case, this is basically a giant mass spectrometer. That's the word I was trying to come up with. It's a giant mass spectrometer. You put your sample in here. There, behind here, it's the best piece. It's the best part name I've ever come across in the course of doing lab work. Get this, right? The part that generates the ion beam that interacts with your sample and then sends the ions that way to be measured. The thing that generates that beam is called the Duoplasmatron, which sounds like it ought to be on Star Trek, right? Anyway, so it hits your sample there and it sends the ions down here. It goes around this magnet. So the magnet then spreads the different mass ions out a little bit. I mean, we're talking about like the difference between uranium-235 and uranium-238. It's very small differences. And then you collect those, the totals down at the end in these collector cups, and you run everything from the computer bank over here. You can see this, the orangish image that's in the middle, that's a picture of a zircon crystal with 3 analysis spots in it. So that crystal is probably 100 microns long. So that's like a sand grain. So we've got a sand grain blown up on the screen, and we've used the ion beam over here to pinpoint the spot we want to hit on that zircon crystal. And that will give us a ratio of uranium to lead that we can use to calculate an age. So these are the zircon, these are called cathodoluminescence images. So zircon and quartz happen to have this weird, it's an optical or an energy phenomenon of it luminesces with a particular wavelength of energy bombarding it. So the cathodoluminescence sends that energy waves at the zircon, and it luminesces. So it gives off light that lets you see the internal zonation in the crystal. And that way you can say, all right, this inner part, like this really dark inner part, is the seed that started the growth of the crystal. And then there's this part here that has there's very faint lines here. Those lines are called, those lines tell you, the concentric rings tell you that it crystallized from a melt, from a magma. And then it probably underwent some sort of metamorphism afterwards. And so you get like 3 age domains within this crystal. Here they've analyzed if you think it, and we talk about it like this is like the core, the mantle, and the rim. We don't say crust. Core, mantle, rim of the crystal. You can, like here, this one is targeting the metamorphic domain of the crystal. So hopefully you'll get an age for when metamorphism happened. Here with the spot within that lighter domain, that's probably going to tell you when a melt crystallized. And then even older, oftentimes you got like 1.8 billion year cores to these crystals. It's crazy. It gives you like an original age of formation of that continent, basically. So it's a really cool technique. The ability to target each of those domains makes it a really powerful tool. And I've used this a lot of times to date processes. In fact, that ties back to the very first picture I showed you. In fact, it ties back to the Himalaya. That's kind of how I got started working in the Himalayas. Was an Indian colleague of mine had zircons that he found I worked on this shrimp, and that I was working on similar rocks to him. And he had these rocks that were from the collision zone between India and Asia, like right in the collision zone. And he wanted to send me the zircons to date. And I was like, that could get me a trip to the Himalaya one day if I work this right. And it did. I've been like 8 times now. So it worked out. Anyway, that work ended up being it's a well-cited paper. It's been cited more than 400 times. And it basically gives an estimate for the age of the India-Asia collision. And so anyone working in the Himalaya or Tibet might cite my paper. So that's kind of cool, right? Okay, and just to blow this up a little bit, I wanted to show you, so this is from a different mountain belt. This is from the eastern seaboard, the Grenville rocks, the Adirondack Highlands rocks that I was showing you, upstate New York. Similar kind of idea. Here are those cathodoluminescence images of these zircons, and you can see where I dated each of these and the age that I got. That's a sample number, and this is the age. 1,152 million years, plus or minus 13 million years. So that's the error on that age. So this is a 1.1 billion year old zircon. And everything we dated in these rocks, some of the youngest stuff was 969 million years, plus or minus 6 million years. This diagram that is like the middle of the screen shows you it's lead-206 and uranium-238. That is one of the set of isotopes that you would use to actually calculate a uranium-lead age. And on this axis, lead-207 and uranium-235 is a second way to calculate the age of these rocks. And so when you put them together, if you get the same answer using both equations, it should fall on this line right here. It's called a Concordia line. And if, like this one, around 1150, see that big circle? The large circle says it's got a larger error, but it falls smack on that Concordia line, which tells you got the same answer using both of those age equations, which means it's a quality age. It's things like this that I want to explain to you, like how the science is done. And it's pretty cool, and it's done right here. It's just down at Stanford. They installed that shrimp while I was a grad student down there too. So I got to watch the whole process, which was pretty cool. Okay, another thing that I do as part of my group, when we're only in the field usually in the summer when the weather's nice and the rocks aren't covered by snow and all that. But we also use, this is a bulk rock chemistry. So we send rock up to Washington State, and they have a facility up there where they pulverize, they crush the rock, and then put it through X-ray fluorescence. And they also use, the acronym is ICP-MS, which stands for Inductively Coupled Plasma Mass Spectrometry. They point a laser at the powder and they get a chemistry out. So like what's in the powder. So 71.7% silica, 0.59% titanium dioxide. So that gives us the major and the trace elements. We'll get into all that language too. If you haven't had chemistry yet, it's okay. You probably had high school chemistry, and hopefully you talked a little bit about that. But anyway, we use that to then model the rock. So there's a program called Perplex, which is a great name because it is perplexing. But we use that program, we input information about the rock, this chemistry, and we model it at different pressures and temperatures. And so here, can you see the bottom of that axis? I hope you can. Someone tell me in the chat box, please, where it says temperature at the bottom. I just want to make sure you can see it because it's hidden behind my Zoom bar. It gives you, I can see it, good. So between 600 and 1200 degrees Celsius. So this is really deep in the earth. So the rocks are hot. They're not melted yet. They start melting right here. See this blue line? They start melting right around 800 degrees Celsius. And so this whole field over here, melt is present as we're modeling, but we're also modeling all these different minerals, potassium, feldspar, plagioclase, garnet, sillimanite, quartz. So we get an assemblage of minerals that we compare to the actual rock, and then we use the model to help tell us more about that rock. And we can do things like estimate how much melt was there 1 billion years ago. It's a really powerful tool. And we can use it, I mean, this is plotting how much, 5% garnet's right about there. And so we have very small, we only have 1 or 2% garnet in these rocks. So it should fall in this field right here. And so we get more answers. It complements all the field work and the lab work that we do, that thermodynamic modeling. And then it boils down to, and this is my last slide about what I do, and then we'll save just the last 15 minutes to talk about science in general. These are a couple of tectonic cartoons that tell you, that are like reconstructions of the geologic evolution, the tectonic evolution of Eastern North America. And it's a very small scale, but that says 1360 or 90. So 1,390 million years ago. I'm not reading that number very well. It's showing you that you had a continent here, and some oceanic crust that was subducting beneath another small continent, so maybe an island off the coast or a small continent off the coast. And there was, even further, there was another continent over here involved in another subduction zone. And we kind of piece by piece, like get answers. We date some of these rocks so we know what time they should have been forming those magmas there. And so subduction was taking place, in this time frame around, God, I can't read that, 1307. So 100 million, not quite 100 million years later, it's changed. Move forward even further, and you see that finally this continent and that continent have collided. And so we've got a new picture of what's taking place. And then we need an explanation for some other magmas that were produced even later, around 1,200 million years ago. There were these melts, and so we have to explain it by pulling away the lower part of the crust there, the lower part of the lithosphere. This is not important. The details are not important. I just want to show you, like, this is the idea, is to explain plate movements, to understand what was happening and where. And these are large scale processes. These are mega scale processes at the scale of a plate. Any questions about what I do before I move on? Take a breath. Okay. So let me tell you about just a little bit more about the class, and we'll get into the content. We had some funding over the summer so that I and some other faculty and lecturers got together to redesign physical geology and to update the labs and the content to work in an online environment. So we've been thinking about this for months now, and we really think this is going to be like a much better course than it would have been at the end of last semester, much better. We are putting together some cool new lab activities, including that one I told you using Google Earth, that I hope is really going to engage you in learning about the geology. I've told you I want to incorporate the work of a diverse set of scientists. I want to talk about career options. And I definitely want your feedback. I really do want there to be interaction. I hope that you'll start to feel comfortable interrupting me to ask questions and not just use the chat box. Like, you can totally feel okay doing that. Oh, I never told you to call me Mary. Please call me Mary. Everyone in the department is like that. Not the chemists. The chemists are strange. Every department's like got their own little culture. The chemists like to be called doctor and professor, but you can use our first name, so Mary's cool. I'm gonna skip this because that's redundant. Okay, so what are your preconceived notions about what science is? I mean, we've been talking, like, since the pandemic started, science and what is or isn't a scientific fact has been somewhat debated, hasn't it? I hope that you're coming to this class because you want to learn the real science. When it boils down to it, we ought to all be listening to the medical scientists, the epidemiologists, and listening to Fauci, right? How do we know what is a fact? What's interpretation? And how do we decide what is what? We're gonna think a little bit more about that. The pre-lab asks you to think specifically about what's a fact, what's an interpretation. So in the pre-lab, there's a short New York Times article that you're gonna read through, and you're gonna highlight in one color the facts and highlight in the other a different color the interpretation. And so you're gonna go through this and do a mental exercise that uses some evidence of feathers on dinosaurs to get you thinking. I'm curious to know what experiences in your life you've had with geology or things that you associate with geology. I certainly would like to know what you'd like to learn about in this class. We cover so much that I feel like I only leave out some like jargon that you don't need to memorize, but otherwise we cover the basics and really thoroughly. In the survey, when I get it working, I ask you a question about that. Please tell me about your background. I want to know if you had high school or science, or if you went camping every summer in national parks like I did as a kid. I want to hear about that. So please let me know. Or if you have no background whatsoever, I want to know that too. What's something about how Earth works that you're curious about? So think about that, and in the survey, please tell me. And again, if you want to draw a picture instead of explain it in words, you can always draw a picture. Okay. These are the learning objectives, and I put this in here. This is for chapter 1. These are the learning objectives for chapter 1. I only put this here. This is not what I'm going to talk about necessarily. A little bit of it, especially with the pre-lab, we'll go into this. But the text differs. So I just want you to understand that, that they're complementary sets of pieces of learning that you're going to have from the text and from me directly. Oh, that's a duplicate. Okay, so why study geology? In the last few minutes of class, we're not going to get into much of the content today. I'll save that maybe to Intro Thursday, or we'll just save it for next Tuesday. So why study geology? There are amazing places this is a picture of Yosemite Valley. That's El Capitan there. That's Half Dome. Have people been? Can I just see of the people whose faces I can see? Can you see a show of hands of who's been to Yosemite before? Some. Yeah. You can always vote. That's another thing you can do in the chat box. Does it let you? I think it lets you raise your hand. Anyway, that's great. Some people have. It's a beautiful place. I highly recommend it. how did that form? We have a giant granite batholith. That means it's just a huge pile of granite that is exposed there. And glaciers have come through and cut this valley a long time later. So these granites were forming between, let's say, 180 million years and 90 million years ago. There are a lot of different smaller plutons that have formed together to make this large batholith. I'm just getting used to some of the terminology. And then maybe 120,000 years ago, glaciers came through and cut that valley. We're going to talk about those glacial and interglacial periods, and we'll certainly talk about the mountain building itself. I've lost my slide. There we are. Okay, volcanoes. This is a trip that we took in our department several years ago. I think it was 2007, 8, somewhere in there. We went to Chile. There was this volcano, I don't remember its name, was erupting at the time. It was so cool. This black layer here is all ash that was laid down. And like this fresh stuff, this fresh black stuff are lava flows from the night before. Oh, and there it is, sort of smoking in the back. We'll talk about where do volcanoes form, what makes them active, what controls whether they're explosive. Is there a volcanic region that you've thought of visiting, or maybe you visited some of these? My top choice is Iceland. That's on my bucket list. I've seen Hawaii, I've seen the Andes, I've seen the Cascades. I haven't been to Japan, so Mount Fuji is also another one. We're going to talk about all these places, and I'm going to explain the geology in all of these places and many, many more. So I just want you to realize that if you see a favorite spot that you want to travel, it's probably got some interesting geology going on. This is from the drive down to Paso Robles. If you ever drove into Central California or Southern California, you've gone past these oil derricks that are rocking if they're actively pumping. We're going to talk about fossil fuels and renewable versus non-renewable energy sources. Surface water, these are some rivers and a hot spring there. There's an interplay there of the landform, the topography. There's an interaction with underground heat sources like a magma body to give you a hot spring, or groundwater also to give you the hot spring. So there are lots of different ways we'll bring this in. This is Pacifica. So just south of the city. It doesn't look like this anymore. These buildings are long gone. You see this chunk of earth was about to fall in too. All this coastal wave action, especially during storms in the wintertime, is eroding our California coast. That's why we have these steep cliffs that you got to hike down to get to the beaches a lot of times. It's the coastal erosion and also our earthquake faults. So like the San Andreas Fault and the Hayward Fault are helping to lift up the coastline compared to the ocean crust there. We're going to talk about earthquakes. This is the aftermath of Haiti in 2010. This is getting to be quite a while ago, but that's good. We don't want disastrous earthquakes very often. But why do some places have more earthquakes than others? What makes the earthquakes dangerous? What are the key ingredients? We'll talk about that, and pretty soon. I'm going to talk certainly about the faults that are in the Bay Area. This map shows San Francisco here. Hopefully you guys can look at a map like this and pick up where you are already. We're going to do a lot more map reading right away to get you started with that. This is the San Andreas Fault there. Here's the Hayward Fault. This is the Calaveras there. And some other named faults. These are other named faults that's Rogers Creek. Green Valley Fault is back here. All together, these form the plate boundary between the North American continental crust and the Pacific plate that is oceanic crust. So there's a wide, it's the width of the Bay Area is the zone of deformation that we're going through to, oh, I'm just keeping track of the time, that helps that is deforming when the plates are moving against one another. We're gonna talk about, there's some glaciers down here in this picture. See right here, there's a glacier, it's covered by rock, so it's a little bit dirty looking. Here's a second one that's joining it. Some other glacial valleys in here. So we're going to talk about deserts and desert processes, wind-driven processes. We'll look at glaciers and the hard work that the ice does in glaciers to erode rock. And we'll talk about climate change. We're going to look at some fossils to think about what the evidence is for how old the Earth is. Here's some, this is an ammonite. It looks like this curled shell right there. So like a squid, but a curled squid shell. How old is the Earth? How has life changed through time? And how have we used that and the different layers of rock to determine the geologic time scale? There's some interesting stories there. I realize our time is almost up. Let me just say the last few things. So I want you to get used to seeing a map of the world, to looking at it, seeing the topography on land, the bathymetry, the shape of what's underneath our ocean, so the form of the ocean floor. There's a lot of information contained there that tells us about plate tectonics. Probably you've heard of the breakup of Pangaea and seen things like this mid-Atlantic ridge that has separated Africa from South America, and boy, don't those continents look like they fit right together. So we'll discuss that. That's talked about in your reading too. Let's stop there because it's noon. I will post the slides that we've gotten to so far, and I'll post this recording right after class. But because it's noon, I'm going to stop. I'm going to remind you about the pre-lab, and I'll be here for a half an hour. I'll just hang out and take questions. If you need a permit number from me, if you need help with iLearn, whatever it is, hang out and we can talk. Otherwise, I'll see you guys on Thursday. Nice meeting you today.
Thank you.
Thank you.
Thanks.